deep beneath the ocean's surface lies a hidden world of energy, where over a third of the world's oil supply is sourced. Offshore oil rigs, architectural giants standing in the middle of the sea, are more than just feats of engineering. They are pivotal in meeting global energy demands. The journey of offshore oil production began in 1897 with a modest operation off the coast of California, and today it has evolved into a high-stakes, technologically advanced endeavor. These operations take place in some of the most inhospitable environments on Earth, often in waters hundreds of meters deep. The complexities of extracting oil from beneath the ocean floor require not only advanced technology and engineering, but also a deep understanding of marine geology and environmental stewardship. With the risks of deep-sea drilling come stringent safety measures and innovative techniques to minimize environmental impact. This intricate dance of technology, human expertise, and nature's forces highlights the remarkable journey of oil from ocean depths to our daily lives. So how do they do it? The primary raw material in offshore oil production is crude oil, a naturally occurring unrefined petroleum product composed of hydrocarbon deposits and other organic materials. This oil is found in reservoirs beneath the ocean floor, trapped in rock formations that have accumulated over millions of years. The location and accessibility of these reservoirs are determined through extensive geological surveys and seismic research. Before drilling can commence, oil companies conduct detailed explorations to identify potential oil fields. This involves the use of sophisticated technology, such as seismic vessels, that send sound waves deep into the ocean bed. The echoes of these sound waves are captured and analyzed to create a map of the geological formations beneath the seafloor, indicating where oil deposits might be located. The quality of the crude oil varies significantly depending on its geographical origin. Characteristics such as density and sulfur content determine the oil's grade and its subsequent market value. Lighter, low-sulfur oil, often termed as sweet crude, is typically more desirable because it yields a higher percentage of high-value products like gasoline and diesel after refining. In addition to crude oil, natural gas is often found in conjunction with oil deposits and is considered a valuable raw material in its own right. Natural gas can be used for energy production or as a raw material in chemical processes, adding economic value to offshore drilling operations. The extraction of these raw materials from the ocean bed requires a combination of advanced drilling equipment and skilled personnel. The process begins with the establishment of an offshore drilling rig, a massive structure equipped with facilities for drilling wells, extracting oil and gas, and temporarily storing the extracted materials. These rigs are marvels of modern engineering, designed to withstand harsh ocean conditions and operate efficiently in remote and challenging environments. The initial processing of oil on an offshore rig is a critical step in transforming the crude material extracted from beneath the seafloor into a form that can be further refined onshore. This phase begins as soon as the oil is brought to the surface and involves several key processes to stabilize and prepare it for transportation. Firstly, the oil undergoes separation. This process involves separating the crude oil from natural gas, water, and sediments. In most offshore rigs, this is achieved using a three-phase separator, a vessel that uses gravity to separate the oil, water, and gas based on their different densities. The gas rises to the top, the oil settles in the middle, and water and sediments drop to the bottom. The separated gas, often referred to as associated gas, can be further processed on the rig, flared, or re-injected into the reservoir to maintain pressure. After separation, the oil undergoes dehydration and desalting. Dehydration removes any remaining water, which is crucial to prevent corrosion in pipelines and storage tanks. Desalting, typically achieved through electrostatic treaters, removes dissolved salts that could cause issues during refining. In this process, water droplets and salts are coalesced and settled out of the oil, The next step is stabilizing the crude oil. This involves reducing the vapor pressure of the oil by removing lighter hydrocarbon fractions to make it safe for storage and transport. Stabilization ensures that the oil does not release harmful gases or explode during transportation. Temperature control is another vital aspect of initial processing. Heating or cooling systems are used to maintain the oil at an optimal temperature, facilitating effective separation and transportation. This is particularly important in regions with extreme temperatures. Throughout these processes, safety and environmental controls are paramount. Offshore rigs are equipped with safety systems to detect and contain any leaks or spills. Gas that cannot be processed or re-injected is burned in controlled flares to minimize environmental impact. Once initial processing is completed, the stabilized crude oil is stored in tanks on the rig. It is then transferred to tanker ships or sent through underwater pipelines to onshore facilities for further refining and processing. This initial phase is crucial in ensuring the quality and safety of the oil before it embarks on its journey to the refinery. The main manufacturing process in offshore oil production, often referred to as the extraction process, encompasses several complex and interlinked stages. This process involves drilling, extraction, and the transportation of crude oil from the ocean depths to the surface, followed by its onward journey to refineries. The process begins with drilling the well. Offshore rigs, either floating or fixed to the ocean floor, are equipped with a drill that penetrates the seabed. Drilling starts with a pilot hole, which is gradually widened using larger drill bits. Drilling fluid, or mud, is circulated through the drill pipe to the drill bit, serving multiple purposes. It cools the drill bit, cleans the drilled rock, and maintains pressure in the well to prevent blowouts. During drilling, several layers of casing are inserted into the well for stabilization and to protect against leaks into the surrounding seabed. Cement is pumped down the drill pipe and up the gap between the pipe and the hole to secure the casing in place. Once the oil-bearing formation is reached, the process of extraction begins. This involves creating a path for the oil to flow into the wellbore. Perforating guns are used to create holes in the casing, allowing oil to flow from the reservoir into the well. Extraction is aided by natural reservoir pressure, but in cases where pressure is low, artificial lift technologies like pumps are used. To enhance recovery, secondary and tertiary methods might be employed. Water or gas injection, known as secondary recovery, helps maintain reservoir pressure. Tertiary methods, or enhanced oil recovery, EOR, involve injecting substances like carbon dioxide or chemicals to reduce oil viscosity and improve flow. Once extracted, the oil undergoes initial processing on the rig, as described earlier. This includes separating the oil from gas and water, dehydration, desalting, and stabilization. These processes are crucial for making the oil safe and stable for transportation. Transporting the processed oil from the rig to shore-based facilities is the next crucial stage. There are two primary methods: tanker ships and subsea pipelines. Tankers are used in more remote locations where pipelines are not feasible. The oil is transferred to the tanker via floating hoses or loading arms. For rigs closer to shore, subsea pipelines directly transport the oil to refineries or storage facilities on land. Throughout the manufacturing process, safety and environmental protection are of paramount importance. Offshore rigs are equipped with blowout preventers, BOPs, to deal with sudden pressure surges. Regular maintenance, safety drills, and strict adherence to international standards and regulations are integral to preventing accidents and spillages. Additionally, monitoring systems are in place to detect any environmental disturbances, such as oil leaks or gas emissions. In the event of a spill, response strategies include containment booms, skimmers, and dispersants to mitigate environmental impact. Technological advancements have significantly improved the efficiency and safety of offshore oil production. These include automated drilling systems, advanced seismic imaging for better exploration, and remotely operated vehicles, ROVs, for underwater inspections and repairs. At the end of a field's productive life, decommissioning takes place. This involves plugging wells, dismantling infrastructure, and restoring the marine environment. Rig-to-reef programs, where obsolete rigs are converted into artificial reefs, are examples of innovative approaches to decommissioning. Offshore oil production is an intricate and highly technical process, starting with geological explorations to identify potential reservoirs beneath the ocean floor. Advanced drilling techniques and state-of-the-art rigs extract the crude oil, which then undergoes initial processing to separate, dehydrate, desalt, and stabilize it. The oil is then transported, either via pipelines or tanker ships, to onshore refineries. This entire operation combines engineering prowess, environmental stewardship, and rigorous safety practices to harness a vital energy resource. It's a testament to human ingenuity in meeting global energy demands while facing the challenges of deep-sea environments and environmental sustainability. YouTube thinks you will like these videos. Have a look and see what you think.